Alright, lesson 8 today, another classifier algorithm which is called support vector machines. And we also will talk about kernel functions. Usually these two are linked. Yeah? Support vector machines were officially introduced to the world by Vladimir Vapnik in 1994. But it's funny because Vapnik already invented the algorithm in the 60s. Just it took him so long to get it known to the world for different circumstances. It's a very popular algorithm. It's very powerful. Yeah? It was so powerful that in the second half of the 90s and in the early 2000s, all papers, all new research was focused on SVMs. And it pushed actually everything which had to do with neural networks to the side. Yeah? So that's why we have a second AI winter in the period between 1994 and about 2006, when Jeff Hinton actually rebranded the perceptron into deep learning. Just want to give you an overview again of where we are. We've seen 4 classification algorithms already: k-nearest neighbors, perceptron, naive Bayes, logistic regression. Today we're going to deal with SVMs and kernels. And then before we embark on decision trees and neural networks, we'll have some intermezzo on regularization and bias variance, especially the trade-off between bias and variance. Okay, let's start with SVMs. And basically this you should remember from our perceptron lesson. You know, a perceptron is able to find a hyperplane H that actually separates 2 classes of data, the positive and the negative class. And remember, there was this perceptron convergence theorem that says that if the data is linearly separable, you will find a hyperplane. And even more, you will find many hyperplanes. Actually, an infinitely amount of hyperplanes that separates the data. And that's true because I could have had this one. Or this one. Yeah? There's many hyperplanes possible. Yeah? So of course this triggers a question is, what's now the best hyperplane? Well, and that's the whole idea of SVMs. The best hyperplane is the one that gives you the highest margin. Yeah? And the margin, let me try to draw it. Would be something like this. You take the minus point closest to the red line, and here the plus point closest to the red line. And so this is here, this is your margin. Okay? And support vector machine tries to maximize that margin. Now we have some notations, of course. We have a vector W, and a vector W here is a unit vector. So it's basically the vector divided by its norm. We've seen that in linear algebra refresher. And then the distance between the origin 2, we will call the middle line, we will call the median. Yeah. Then we know that on the hyperplane from the perceptron, W transpose X plus B equals 0. We know that from the perceptron. And that's basically it. With this we can start. First of all, we know that W should be perpendicular to the hyperplane H as well. Yeah? We can prove that. Suppose you have 2 points. Yeah, I would say on the hyperplane. Yeah, that means that W transpose x1 plus b equals 0. Yeah. You have another point, let's say x2 plus b equals 0. And now when you subtract them from each other, you have that w transpose x1 minus w transpose x2 equals 0. Yeah, so that means that w transpose x1 minus x2 equals 0. Yeah, and a dot product meaning 0 means that w transpose is perpendicular to x1 minus x2. But x1 minus x2 is a point on the hyperplane, because they're both on the hyperplane. So with this we've proven that the vector or the unit vector w here is perpendicular to the hyperplane h.